To move a machine, we must translate a discrete digital coordinate, x, y, z, roll, pitch, yaw, into physical mechanical actuation. Solving this translation problem requires breaking down the physical architecture of a standard 6-axis robotic arm into distinct hardware components. At the very tip of the assembly is the end effector. This is the specific tool, whether a gripper or a welding torch, that directly interacts with the environment. Controlling its position relies on the joints. These are the mechanical articulation points that provide the arm with its degrees of freedom. Connecting these joints are the links. These rigid structural spans physically transfer motion from one articulation point to the next. To monitor this hardware in space, the system relies on sensors. These provide the real-time environmental feedback necessary to track precisely where the arm is located. Commanding this chain of hardware components to reach a highly specific target coordinate requires a robust mathematical framework. In robotics, this framework is called inverse kinematics. To structure these complex calculations, developers use the Robot Operating System, or ROS, which serves as the foundational software architecture. Within ROS, the primary toolset utilized in methodologies at Royal Research is the MoveIt framework. MoveIt provides a dedicated abstraction layer designed specifically to automate and optimize the entire motion planning pipeline. Without the computational bridge of inverse kinematics and MoveIt, robotic hardware remains rigid, inert metal. With it, the hardware gains the capacity for dynamic, autonomous manipulation. To understand the computational heavy lifting involved, we have to establish the baseline of forward kinematics. Forward kinematics is computationally straightforward. If you input a set of known joint angles, the math reliably outputs one highly predictable position for the end effector. Inverse kinematics works in exactly the opposite direction. The desired position for the end effector is known, but the specific joint angles required to get there are unknown variables. This reversal introduces a major mathematical roadblock. Inverse kinematics is a highly nonlinear problem. A single spatial coordinate can often be reached through several valid joint configurations. However, physical hardware constraints, like joint rotation limits, instantly invalidate many of these possible solutions. Furthermore, if a target coordinate is physically out of reach, the equation yields 0 valid solutions. Manually calculating these nonlinear equations and filtering through multiple configurations in real time carries an immense computational cost. Attempting this manual calculation while strictly avoiding hardware limits creates a processing bottleneck. Safely driving the robot at operational speeds requires a dedicated algorithmic solver. This bottleneck is exactly what the MoveIt framework resolves for roboticists at Royal Research. It acts as an open-source abstraction layer that calculates these inverse kinematics within the ROS environment. The pipeline begins by defining the robot model. Developers create a strict digital map of the physical joints, links, and specific kinematic plugins that dictate how the machine can move. This diagram illustrates the next step, the planning scene. This maps the environment, establishing spatial boundaries and plotting static obstacles around the robotic base. Sensor data continuously feeds into the scene, allowing the system to track dynamic, moving obstacles in real time. With the environment mapped, MoveIt transitions to the plan and execute phase. It utilizes the Open Motion Planning Library, or OMPL, as its core algorithmic engine to compute the physical path. OMPL generates a smooth trajectory that satisfies both the designated target coordinate and the strict mechanical limits of the hardware. Calculating a path is only half the process. MoveIt applies an iterative safety mechanism through real-time collision detection. Before allowing any physical movement, the framework continuously checks the OMPL-generated path against the obstacles mapped within the planning scene. The software also performs path optimization. It finds a viable path and then calculates the most geometrically and mechanically efficient route available. The final execution step transmits that optimized, verified trajectory down to the hardware controller for physical actuation. MoveIt takes isolated mathematical models and raw sensor inputs and fuses them into a single, mathematically guaranteed, collision-free hardware command. To ensure this complex pipeline operates correctly, developers use RViz, the standard 3D visualization tool natively integrated with ROS and MoveIt. This simulated interface shows how RViz serves a critical diagnostic function, allowing engineers to visually simulate and debug kinematic calculations before engaging physical hardware. This validation completes a unified data flow pipeline. The flow begins with continuous sensor input capturing the layout of the physical environment. In the second phase, MoveIt and OMPL process that incoming data to solve the inverse kinematics problem and plot an optimal path. Finally, the physical controller executes the exact maneuver verified in the simulation. Running this flow through a simulation first prevents catastrophic physical damage to the hardware caused by mathematical errors or unexpected collisions. The strict simulation-first methodologies deployed by institutions like Royal Research rely entirely on this precise integration of ROS and MoveIt. This highly dynamic software approach replaces older legacy robotics, which relied entirely on rigid, repetitive, and blind assembly programming. By utilizing real-time motion planning, modern robotic arms instantly adapt to extreme, unpredictable variations in their operational space. This adaptability makes high-stakes applications possible, like executing delicate, microscopic surgical procedures or managing highly variable advanced manufacturing lines. Mastering the mathematics of inverse kinematics and the architecture of the MoveIt framework grants robotic systems the spatial intelligence required to interact safely with an unpredictable physical world.